Swayam Prabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The topic of today's session is virtual machine migration, or it is also called as a VM migration. Preface. Content of this lecture. In this lecture, we will discuss hotspot mitigation techniques that is being used in virtual machine migration, that is VM migration, to automate the task of monitoring and detecting the hotspots by determining the new mapping of physical to the virtual resources and initiating the necessary migration. We will discuss a specific technique which is called a black box approach, that is fully operating system and application agnostic, and a gray box approach that exploits the operating system and application level statistics. Meaning to say that we will introduce you first what do you mean by the virtual machine migration, and then how the virtual machine migration is done, what is the method for that, and then we will see that what is the application of the virtual machine migration in automation of the today's cloud system. So, inside cloud, you know that there are some physical machine which are or servers which are overloaded, and they are called hotspots. So, those physical machines which are overloaded, they are called hotspots. Some of the virtual machine, if they can be migrated, then it will give a good load balancing, and thereby the cloud computing can run with a less memory, with a less energy and more capacity in this particular manner. So, we are going to see that this particular technique, which is called a hotspot mitigation, is going to make this cloud system automated without manual intervention. We will see all that in virtual machine migration. So, the key technology of automating the cloud computing system is called virtual machine migration. We are going to see that virtual machine migration. So, virtual machine migration is not only used in the cloud system, but now in the design of edge computing system, it is very much useful. So, in the today's edge computing system, this virtual machine migration is also one of the key technique. So, we are going to see this important lecture which is called a virtual machine migration. So, let us get started by looking up the enterprise data centers. So, enterprise data centers are often found in the cloud data centers, also called a cloud data centers. Now, here these cloud data centers are composed of the large clusters of servers. Here you can see this is a large cluster of servers, and the network attached storage devices. In some of the cases, it will be a network attached storage devices. So, this is called a data center. This picture is a view of the cloud data center, or we call it as data center. Why? Because this type of scenario is also there in the edge data center. So, edge data centers are little smaller in compared to the cloud data center. So, these data centers are either the cloud data center or edge data center. These particular data center comprises of large number of clusters of servers, and cluster of servers means that more than several servers are grouped together, they form a cluster, and large clusters of servers are there inside data center. So, data center is comprised of large cluster of servers and network attached storage devices. Now, in this particular data centers, we have multiple applications running per server. Now, for this you require the shared hosting environment, and multi-tier may span multiple servers. So, meaning to say that you have seen in the previous lecture about the virtualization technologies. This virtualization technology allows the sharing of server across virtual machines which are running different applications. So, therefore, multiple application per server is a reality, and that is done with the help of virtual machines. So, this brings up the shared hosting environment, and the example of this particular data center is an ideal representation of shared hosting environment, where the servers are being shared by multiple applications. Now, here it is multi-tier may span multiple servers and allocates the resources to meet the service level agreements. So, meaning to say that the applications are assigned or allocated the resources. When we say resources, we mean the CPU, memory and the network. These resources are allocated to different applications, and these applications will use these resources with a strict agreement, that is called service level agreement, to meet the service level agreement. So, this will ensure the quality of service guarantees based on the resources which are being allocated to these particular thing, and virtualization is increasingly common. Therefore, in enterprise data center, let us summarize. In enterprise data centers, the most important part is that the data center comprises of large number of servers. Second important thing is that the multiple applications per server is running, that is the server consolidation. Is the norm, where multiple applications may run in a server. Third thing is, this is done with the help of virtualization. Virtualization allows sharing among multiple applications. Fourth one is that these resources which are allocated to the applications, they have to follow strict service level agreement. So, the resources allocated to the applications meets a strict service level agreement. These together technologies is called the data center. So, data center is having the large number of servers and often network attached storage devices, one part. The other part is that multiple applications per server can execute, and this is called the shared hosting environment, and the technology which facilitates this sharing of a physical machine over to run multiple applications in a shared manner, that is to allow the shared hosting environment. The key technology is the virtualization. and allocation of resources in this manner, that is to the virtual machines, is strictly has to follow some kind of agreement, that is called service level agreements. All these things together is the requirement of running a data center, and that is called an enterprise data center. Now, let us see that if let us say that running or hosting multiple application on a same machine is done through the virtualization. So, let us see what are the benefit of the virtualization. So, virtualization run multiple application on one physical machine, that is on one server, where each application is running in its own virtual machine. So, meaning to say that the virtual machine or physical machines can allows sharing or allows the execution of several virtual machines, and each virtual machine will run its own application. Applications will run on virtual machines. So, maybe this will implies that the physical machine is now hosting to run multiple applications. The next benefit is that it maintains the isolation. Isolation means if this is the physical machine and multiple virtual machines are running 1, 2, 3, 4, 5, then virtual machine 1 will be isolated from virtual machine 2 execution, they will not interfere, hence they will maintain the isolation. Another important thing is they provide the security, that means virtual machine 1 and 2, if they are simultaneously running and coexist, then both of them will follow their own security norms and maintains the isolation. Now, another benefit of the virtualization is that it rapidly adjusts the resource allocations, that is the CPU priority, memory allocation and so on. Most important part of the virtual machine is the virtual machine migration. Virtualization allows the virtual machine migration. This virtual machine migration is transparent to the application, and this will also ensure that there is no downtime and also incurs some kind of overhead. So, for example, if this is the physical machine which is running two virtual machines VM1, VM2, and this is another physical machine, let us say PM2, which is running a physical virtual machine 3. Now, if this particular virtual machine is going down due to some regions, let us say it is down due to some region, then this particular virtual machine can be migrated here VM3 to run on physical machine 1. So, this is called migration, VM migration. So, this VM migration ensures no downtime. Although the physical machine 2 is down. So, the services will continue to operate due to the virtual machine migration, but incurs a little overhead of virtual machine migration. Now, the question is how can we use virtualization to make more efficiently utilize the data center resources. So, let us see about the data center workloads. Now, take the example of a web applications, enterprise systems, e-commerce sites, and all of them, these applications see a dynamic workloads. So, dynamic workloads often fluctuates and they are caused by the incremental growth, time of the day effects and flash crowds, etc. So, here you can see that time of the day, if you see this particular load and the requests which are coming, these load often fluctuates. So, here this is a fluctuating Here this is a fluctuating workload scenario, and here this is the effect which is called time of the day. In a particular day there is a peak hours and normal hours or a downtime or a low hour means low traffic and so on. So, this particular type of workload is often means this particular data center is designed to accommodate different type of applications, different type of workloads which are dynamic workloads which are fluctuating caused by incremental growth, time of the day effects, splash cloud and so on. They are called data center workloads. So, how can we provision the resources to meet these changing demands while meeting the service level agreement becomes a quite complex in data center operations. So, let us see that what are the different provisioning methods are there. Now, let us see that the hotspots will form if the resource demand exceeds the provision capacity. Over provisioning, this particular approach that you allocate for the peak load, then in that case it will waste the resources. For example, peak load if you see it is not always there. So, it is not suitable for a dynamic workloads over provisioning, and therefore, also very difficult to predict the peak resource requirement in most of the cases. Now, another solution here is dynamic provisioning. Here we have to adjust based on the workload, often done manually and become easier with the virtualization. Let us see some of the problem statement and we will see the use case and we will understand about virtual machine migration in solving these problems in the data center operations. So, the problem statement says that how can we automatically monitor for the resource usage, how we can we automatically do the hotspot detection and how we automatically can mitigation, that is determining the new mapping and initiating the necessary migration, that is to detect and mitigate the hotspot in a virtual machine in a virtualized data center environment. So, let us see some of use cases that is called hotspot mitigation and how the virtual machine migration is going to solve this in a virtualized data center. So, once a hotspot has been detected, what is an hotspot? First of all, we have to understand a particular physical server or a physical machine is experiencing lot of load of a virtual machines. All the virtual machines are bringing up too much of load, virtual machine 1, 2, 3, 4. So, this particular physical machine is having the shortage of available resources, most of the resources are heavily overused and this is called the hotspot. So, once these particular machines are directed into the data centers, they are called hotspots. Then what we have to do is we have to identify the new allocation where some of the virtual machines can be migrated, so that this particular system or a physical machine can continue normal working with the other virtual machines. So, that means that once the hotspot is directed, the new allocations have been determined for the overloaded virtual machines and the migration manager invokes its hotspot mitigation algorithm. So, this is an example use case. For VM migration. So, this particular algorithm which is called a let us say hotspot mitigation algorithm determines which virtual servers to mitigate and where in order to dissipate the hotspot. So, that means we have to identify in these virtual servers which are called hotspots. In these virtual servers we have to identify those virtual machines which are experiencing or which are contributing into becoming the hotspot or draining out all available resources of that physical machines. So, the responsible virtual machines need to be identified in these machines which are designated or which are identified as the hotspot, and then we have to identify those virtual machines and to mitigate, and where to mitigate in order to dissipate the hotspot, means on which physical machine they will be migrated. So, determining the new mapping of the virtual machines to the physical servers that avoids the threshold violation is often studied as NP complete problem in the large settings such as the virtualized cloud data center. Why? Because it reduces this particular problem, reduces or multidimensional bin packing problem is reduced to this particular problem of determining the new mapping of virtual machines to the physical machine that avoid the threshold violation, and therefore, since multidimensional bin packing is the NP complete problem, therefore, this becomes a NP hard problem where each server is a bin with the dimension corresponding to the resource constraints, and each virtual machine is an object that need to be packed with the equal size of its resource requirement. Even the problem of determining if the valid packing exists is NP hard. So, let us see some of the research challenges here in solving this particular problem or using the virtual machine migration technique. So, the first type of challenge is called hotspot mitigation, that is how automatically we can detect and mitigate the hotspot through virtual machine migration. So, virtual machine migration is the key technology, but identifying automatically to detect and mitigate the hotspot becomes a real difficult problem that we have seen in the previous slides, called NP hard problem. Now, here in the virtual machine migration in hotspot mitigation requires to answer three different questions. Where to migrate means which system, which physical machine is available to accommodate that particular virtual machine on the other physical machine which has become the hotspot. Now, another thing is when to migrate. When to migrate is what is the time when before that if it is not migrated, this particular system will stop functioning, because there will not be any further resource allocation or resources to run in that particular system. So, when to migrate. So, that time is important, where to migrate, when, where to migrate, this is also important, and how much of each of these resource to allocate, that also is a resource requirement. Now, this particular problem hotspot mitigation you can now imagine as the problem of a sandpiper migratory birds. So, migratory birds often migrates from one country to another regions in search of the food and the environment in which they live. So, how much information needed to make these particular decisions? So, let us understand through some background. So, dynamic replication, dynamic provisioning approaches are focused on dynamic replication, where the number of servers allocated to an application is varied. Now, dynamic slicing, in dynamic slicing the fraction of the server allocated to an application is varied, and application migration, that is in virtualization the virtual machine migration is performed for dynamic provisioning, and migration is transparent to the application executing within the virtual machines. Let us see the sandpiper architecture here in the virtual or the hotspot mitigation, and also we will be able to understand the complete details of virtual machine monitor. So, this sandpiper architecture is for hotspot mitigation, framework, and this is to understand virtual machine migration in this context. So, let us see the sandpiper architecture. It will have a nucleus, and nucleus will have the monitor resources, and these monitor resources reports to the control plane, and this particular nucleus is one per server. it runs inside a special virtual server, that is domain 2, and it has a control plane that is called centralized server. Let us trace through all these here in this example. Now, here you can see that this is the physical machine 1, this is physical machine 2, and it is running the Zen hypervisor, that is Zen virtual machine monitor. Now, this physical machine will now have 2 virtual machines, VM1 and VM2 running, that is on physical machine 1, and VM1 is running an Apache application, where VM2 is running the Java application, and in the other part of that same virtualization, it will run a monitoring engine and a nucleus within it. So, as I told you, the monitoring engine and the nucleus will run together in every physical machine. Every physical machine will have a monitoring and the nucleus engine. So, monitoring and nucleus will monitor the resources in the physical machine, and then they will report to the control plane. Now, this is the called control plane. So, this is the Sandpiper control plane. So, this particular control plane is common across all the physical machines. So, let us see that this particular control plane. So, all the information which is sent by the nucleus and the monitoring engine to the control plane will run 3 different modules. One is called profiling engine, hotspot detector, and mitigation manager, based on the information which is being collected from physical machines, which is running the nucleus and the monitoring engine. So, let us see that inside control plane you will have hotspot detector, detect when a hotspot occurs based on the statistics which are the information which monitoring engine and in its nucleus sends to the control plane. The other one is called the profiling engine, will decide how much to allocate. Third one is called migration manager, and migration manager determines where to migrate. So, once the hotspot is detected, then the migration has to now look upon the others through the that means to the other physical machines which has the availability to accept this particular migration of a virtual machine. So, let us see that there are 2 methods to do this. One is called black box, the other is called a gray box. So, black box means that only the data from outside the virtual machines can be visualized. So, in the black box means you cannot see inside the virtual machine. From the outside, the statistics you collect and get the information about the virtual machine. It is completely operating system and application agnostic, that is called black box approach. The other method that says that it called gray box, here it is accessible, it is having an access to the application logs and operating system statistics, and through these information it will be able to make out the inference about that particular virtual machine, and this is called the gray box. So, gray box accesses the operating system statistics and application logs. Request level data can improve detection and profiling, and it is not always feasible, because customer may have the control of operating system and sometimes may not allow to inspect inside the virtual machine about some of the applications. So, let us see that if there are 2 methods which are available, how we are going to see all that. Now, the question is, is this black box sufficient? What do we gain out of the gray box data? So, black box monitoring says that, for example, Zen uses the driver domain special virtual machine with the network and the drivers, and nucleus runs over here, and CPU it will collect the CPU means scheduler statistics, it will collect the network, that is the Linux device information, and it will have the memory information, that is get the swiping from disk IO, and only know when the performance is poor. So, in a black box monitoring, let us see about the memory monitoring. So, black box monitoring of the memory is challenging, since Zen allocates a user specified amount of memory to each virtual machine and requires the operating system within the virtual machine to manage that memory. As a result, the memory utilization is only known to the operating system within the virtual machine. It is possible to instrument Zen to observe the memory accesses within each virtual machine through the use of shadow page table, which is used by Zen's migration mechanism to determine which pages are dirty during the migration. However, trapping each memory access results in a significant application slowdown and is only accessible during the migration. Thus, the memory usage statistic is not directly available and must be inferred. Now, black box monitoring is useful in the scenarios where it is not feasible to peek inside a virtual machine to gather the statistics. Hosting environment, for instance, run third party applications and in some cases third party installed operating system distributions. So, take this example of Amazon's Elastic Compute Cloud EC2 service, for instance, provides a bare bone virtual servers where the customer can load their operating system images. While the operating system instrumentation is not feasible in such environment, and the environments such as corporate data centers where both hardware infrastructure and the applications are owned by the same entity. In such cases, it is feasible to gather operating system statistics as well as the application logs, which can potentially enhance the quality of decision making. So, what is a hotspot? So, hotspot indicates the resource deficit on the underlying physical server to service the collective workloads of the resident virtual machines. So, before hotspot can be resolved through the mitigation, the system must first estimate how much additional resources are needed by the overloaded virtual machine to fulfill their service level agreements. These estimates are then used to locate the servers that have sufficient idle resources, meaning to say that the hotspot indicates the resource deficits on an underlying physical server to service the collective workloads of the resident virtual machines. So, as far as the mitigation is concerned, so mitigation can be resolved with the help of virtual machine migration. So, there the system must first estimate how much additional resources are needed by the overloaded virtual machine to fulfill their service level agreement, and these estimates are then used to locate the servers that have sufficient idle resources. So, hotspot detection algorithm, let us see, is responsible for signaling a need for virtual machine migration whenever SLA violations are detected, implicitly by the black box approach or explicitly by the gray box approach. So, hotspot detection is performed on per physical server basis. In a black box approach, a hotspot is flagged if aggregate CPU or the network utilizations on a physical server exceeds the threshold or if total swap activity exceeds the threshold. Now, in contrast, explicit SLA violation must be detected on a per virtual server basis. In the gray box approach, a hotspot is flagged if the memory utilization of the virtual machine exceeds a threshold or if the response time or the request drop rate exceeds the SLA specified values. Now, to ensure the small transient spike does not trigger the migrations, a hotspot is flagged only if the threshold or SLAs are exceeded for a sustained period of time. Given the time series profile, a hotspot is flagged if at least k out of n most recent observations as well as the next predicted values exceed a threshold. So, with this constraint we can filter out the transient spikes and avoid the needless migrations. So, the value of k and n can be chosen to make the hotspot detection aggressive or conservative. So, for a given n, small values of k can cause aggressive hotspot detection, while the large value of k imply a need for more sustained threshold violation and thus a more conservative approach. So, in the extreme when k is equal to 1 and n is equal to 1 is the most aggressive approach that flags the hotspot as soon as the threshold is exceeded. So, So, we are going to see that in addition to requiring k out of n violation, we also require that the next predicted value exceed the threshold. So, additional requirement ensure that the hotspots is likely to persist in the future based on the current observed trends. Also predictions capture the rising trends while preventing the declining ones from triggering a migration. So, let us see about some of the algorithms, some of the approaches for the hotspot detection. So, it employs the time series prediction techniques to predict the future values. Specifically, the system relies on auto-regressive family of predictors, where nth order predictor, that is called AR of n, uses n prior observations in conjunction with other statistics of the time series to make the prediction. To illustrate, the first order AR 1, that is first order nth order predictor, first order predictor is the first order AR 1 predictor. Let us consider the sequence of observation u 1, u 2 and so on up to u k. Given this time series, we wish to predict the demand in k plus 1th interval, that is in the next interval. Then in the first order predictor, that is AR 1 predictor, makes the prediction using the previous value, that is u k, if let us say that we want to make a prediction of k plus 1th. So, the mean of the time series values of mu and the parameter which captures the variation in the time series. So, the prediction of u k plus 1 is given by mu plus phi of u k minus mu. So, these observations arrive from the nuclei that we have seen in the Sandpiper architecture, that the hotspot detection updates its prediction and performs the above checks to flag the new hotspots in the system. So, here let us see that when we are going to detect the hotspot detection when. So, we have to now understand about the resource thresholds. So, potential hotspots, if the utilization exceeds this particular threshold, only triggers for the sustained overload. So, must be overloaded for k out of n measurements, and auto-regressive time series model can be used. So, it uses the historical data to predict the future values. So, minimize the impact of transient spikes. So, here you can see in this particular figure that here the utilization versus time, in if it is plotted, then you can see that it is moving. This is a spike, it is not detected as the hotspot, because still it is moving and it is considered to be non overloaded. Similarly, this spike is also transient spike, it does not detect as the hotspot. Whereas, here you can see that utilization versus time, here it has reached to a point and is still growing for more demand of the resources which are not available. So, this is detected as the hotspot. So, this auto-regressive time series model is good enough to predict the future values using the historical data, and will be used to detect whether the hotspot is there or it is not overloaded. Let us see the resource provisioning, that is in a black box provisioning. So, provisioning component needs to estimate the peak CPU network and the memory requirement of each overloaded virtual machines. Doing so ensures that the SLAs are not violated even in the presence of the peak workload. So, estimating the peak CPU and network bandwidth needs the distribution profile to estimate the peak CPU and the network bandwidth of each virtual machine. So, the tail of usage distribution represents the peak usage over the recent past and is used to estimate the future peak needs. So, this is achieved by computing a high percentile, that is 95 percentile of the CPU and the network bandwidth distribution as an initial estimate of the peak needs. So, consider this example about this limitation of the black box. Consider two virtual machines. Consider two virtual machines that are assigned the CPU weights 1:1, resulting in a fair share of 50% each. Assume that virtual machine is loaded overloaded, requires 70% of the CPU to meet its peak needs. If virtual machine is underloaded and only 20% of the CPU, then the work conserving Xen scheduler will allocate 70% to virtual machine 1. So, in this case the tail of the observed distribution is good indicator that VM 1's peak needs. In contrast, if VM 2 is using its entire fair share, that is 50%, then VM 1 will be allocated exactly its fair share. In this case the peak observed usage is 50%, and underestimate of the actual peak need, since the system can detect the CPU is fully utilized, it is estimated it will be estimated the peak to be 50 plus. Now, therefore, estimating the peak memory needs here Xen allows the fixed amount of physical memory to be assigned to each resident virtual memory, and this allocation represents a hard upper bound that cannot be exceeding the memory of the demand. Now, consequently, the techniques for estimating the peak CPU and the network usage do not apply to the memory. So, the provisioning component uses observed swap activity to determine if the current memory allocation should be increased. So, if the swap activity exceeds the threshold indicating the memory pressure, then current allocation is deemed insufficient and increased by the constant amount. Since the gray box approach has access to the application level logs, the information contained in the log can be utilized to estimate the peak resource needs of the application. Okay, so here we will skip it, and then we will go for estimating the peak CPU needs. Here in this case, in application model, it is necessary to estimate the peak CPU needs. So, application such as weblogs and database servers can be modeled as the queuing system, and the behavior of such queuing system can be captured using following theory, where D is the mean square, where D is the mean response time of the request, S is the mean service time, and lambda cap is the request arrival rate, and rho square A and rho square 2 are the variance of inter arrival time and the variance of service time respectively. Note that the response time includes of the full queuing delay, while service time only reflects the time spent actively in this particular request. So, here what we have observed is that if this particular factor is greater than 1, if the peak arrival rate exceeds the current provision capacity, thus if the VM is currently assigned CPU weight W, its allocated share need to be scaled up by a factor lambda peak divided by lambda cap to service the peak workload. Estimating the network needs, the peak network bandwidth usage is simply estimated as a product of estimated peak arrival rate, that is lambda peak. So, mean requested file size B, this amount of data transferred over the network to the service the peak load. So, mean request size can be computed from the service logs. So, let us see about the live VM migration stages. So, live VM migration follows the following stages or steps. So, first is that if VM is normally running on the host A, let us say this is the host A, this physical machine, and this particular VM is running on it. Normally on host A, if it is running normally on host A, then let us start with the stage 0, which is pre-migration. So, pre-migration stage says that you have to have an active virtual machine on a host A, and then alternative physical host may be pre-selected for the migration, that is block devices mirrored and free resources are maintained. So, the second stage is called the reservation, that is it initializes a container on the target host. Let us say this is the target host. Then overhead due to copying. So, iterative pre-copying, that is, it will enable the shadow paging, copy the dirty pages in the successive rounds. So, this particular virtual machine will start this iterative pre-copy. Iterative pre-copy means it will enable the shadow paging. So, whatever is modified, copying the dirty pages in the successive rounds. So, enable the shadow paging. So, shadow paging technique will copy the memory from the pre-migration to the reservation or to the target host. Now, next thing is the downtime, when virtual machine will be out of the service over here. So, it will stop and copy. So, it will stop functioning on host A and it will copy all the memory. So, it will suspend the virtual machine in A, it will not further work. It will generate ARP to direct the traffic to the host B, address resolution, synchronize all the remaining virtual machine state, remaining VM state to host B. So, that will synchronize, will copy all of that here in VM will appear, and then stage 4 is the commitment, that means VM state on host A is released, and finally, the stage 4 is the activation, that is VM running normally on the host B. So, now it will start running on host B. So, VM start on host B and connects to the local devices and resumes normal operation. So, these are all live VM migration. So, in live VM migration, you see that if the VM is migrated, so it will continue with a very less interrupt, with a less time when it is down, and otherwise you know that it keeps on in the migration, the services are not stopped. So, live migration stages, pre-migration we begin with an active virtual machine on a physical host A. To speed any future migration, the target host may be pre-selected, where the resources, where the required resources to receive the migration will be guaranteed. So, that target host should ensure that it will continue to give the resources which are required by the system. So, stage 2 is called the reservation. So, a request is issued to migrate from an operating system to host A to host B. So, we confirm that the necessary resources are available on B, that is called reservation. It will perform the reservation of resources. And then we initially confirm that the necessary resources are available on B and reserve the virtual machine container of that size, and failure to secure the reservation means that so this is not applicable. Now, then stage 2 will come, that is called iterative pre-copy. So, during the first iteration all the pages are transferred from A to B. So, this is host A. So, during the first iteration all the pages are transferred, from host A to host B, and subsequent iterations copy only those pages which are dirty during the previous transfer phase. So, all the memory of that virtual machine will be copied over here during the pre-copy phase, and then the virtual machine continues to run. So, whatever pages are dirtied, only those will be copied in the further iterations. So, stop and copy, we suspend the operating system instances at A and redirect the traffic to B as described earlier. CPU state and any other remaining inconsistent memory pages are then transferred. At the end of this stage, there is a consistent suspend suspended copy of the virtual machine at both A and B. So, the copy of A is still considered to be the primary and resumed in case of the failure. Finally, the stage 4 is called commitment. Host B indicates to A that it is successfully received the consistent operating system image, and the host A acknowledges this message as the commitment of the migration transaction. Host A now discards the original virtual machine and host B becomes the primary host. Finally, the activation. So, the migrated virtual machine on B is now activated. Post migration code runs to reattach the device drivers and to the new machine and advertise moved and IP addresses. Now, hotspot mitigation algorithm resorts to the heuristic to determine which overloaded virtual machines to migrate and where such migration overhead is minimized. So, by reducing the amount of data copied over the network, it can minimize the total migration time and thus performance impact on the application that we have already seen. Now, determining the placement, where to do the placement. So, the migrate the virtual machines from overloaded to the underloaded server. For that, it requires a formula which is nothing but a volume is equal to 1 upon 1 minus CPU times 1 upon 1 minus network times 1 minus 1 upon memory. So, you can see that the use volume to find out the most loaded servers. So, captures the load on multiple resource dimensions. Highly loaded servers are to be targeted first. So, migrations occur overhead and migrations cost determined by the RAM and migrate the virtual machines with the highest volume per RAM ratio. So, the virtual machines with the highest volume per RAM ratio will be treated as hotspot. Highest volume per RAM ratio. So, that means we are going to calculate the volume in the following using the following equations: 1 upon CPU, 1 upon net, 1 upon memory. So, this particular equation will calculate the volume, and the highest of volume per RAM ratio will be the virtual machine which is directed as the overloaded. So, maximize the amount of load transferred while minimizing the overhead of migrations. So, let us see the placement algorithm. First, try the migrations. So, displace the virtual machine with the high volume servers, use volume per RAM ratio to minimize the overhead, and then do not create. What if the high average load is there in the system? Then it is swap if it is necessary. Swap a high volume virtual machine to a low volume virtual machine. So, requires 3. So, swap increase the number of hotspots that we can resolve in this particular manner. So, the reading is here, if let us say you want to read this particular strategies for virtual machine migration, and there are black box and gray box strategies are there written in this particular paper, and live VM migration of virtual machines is there in other paper which is shown over here. So, conclusion. So, virtual machine migration is a viable tool for dynamic data center provisioning. Not only that, it has many other application in edge computing and the cloud computing automation. Now, in this lecture we have discussed an approach to rapidly detect and eliminate the hotspots while treating each virtual machine as the black box. Gray box information can improve the performance in some scenario, that is through the proactive memory allocations. So, the future work in this direction is that here that the black box memory monitoring can be further improved, or support for replicated services, and these type of systems are very much useful to understand the need for virtual machine migration use cases, and such use cases are being found in not only in the cloud and also in the edge computing systems. Thank you very much.